Hi everybody. In this video, I wanted to do an example from chapter 24. First of all, of calculating the electric potential from a continuous charge distribution. Now in the problems we had last week for electric field and electric potential this week, it's a line charge. But in this particular situation, we're going to do a different configuration of the continuous charge. And that configuration is a hoop. So you can see what I've tried to draw here is a hoop or a circle of charge, right? A very thin circle. So it's kind of like a line charge in the form of a circle. And I want to calculate the electric potential at a point P, a distance Z directly above the center of that circle. So all of the charge is on the circle, and you can see, right, we're going to have to do an integral over all of those little infinitesimal source charges, dq. Now if I slice up the whole circumference of the circle, I get what I call ds, so a little slice of the arc length. The radius here is capital R from the center of the circle to where the charges are. So again, my plan is to write the expression for a point charge, right, dq, but I've got a whole bunch and I have to add up all of those point charge potentials at the point P here. So first of all, some geometry, r squared, the distance between the point charge dq and the point P is r. R squared is square root of the radius squared plus z squared, right, Pythagoras' theorem. Once again, like for a straight line of charge, we use a charge density, a linear charge density here. And we take the total charge on the hoop divided by the whole length, or arc length, which is just the circumference, 2 pi r. Now, if we want to look at each infinitesimal slice, once again, we've got lambda, charge density equals dq over ds. But ds is r d theta, right? If arc length is angle or radius times angle, as long as we're using radians to describe the angle. So again, kind of like we did for electric field, we start with the expression for the electric potential of a point charge, k dq over r. Electric field, remember, was kq over r squared. Now the other difference here, and this makes things easier, is that electric potential is a scalar quantity. It's not a vector. It has no direction. So I don't have to worry about the direction of the field or anything there. I just have to do this integral. So basically, what I'm going to end up doing is kind of what I did before for line charges. dq is equal to lambda ds, or lambda r d theta. Right? And I'm going to plug in the expression for r here. Sorry, this shouldn't be r squared, it should be r, right? R is the square root of r squared plus c squared. So plugging all of that stuff in, dq equals lambda r d theta, r equals square root of capital R squared plus z squared, I get this. Integral goes over the angle from 0 to 2 pi, all the way around the circle. Now, all of this stuff is constant, right? The integration variable is theta, so everything else in here is a constant, and it can just be pulled right out of the integral. So the integral is actually easy. Integral from 0 to 2 pi over d theta is just 2 pi. So I end up with my final expression here for the electric potential at that point P, just 2 pi k lambda r over square root of r squared plus z squared. Now, I could go back and use that lambda is capital Q over 2 pi r, plug that in, and get this expression, kq over square root of r squared plus z squared. Pretty simple expression for the electric potential, and again, it does not have a direction. Now, the next question you might ask is, can I get the electric field from this electric potential? And the answer is yes. It turns out the electric field is related to the derivative of the potential. In fact, if you have a one-dimensional thing, right, it'll be that the electric field is negative dV dz. Right, my variable here is z Now the electric field, we should guess it's going to point upward, right? But generally speaking, you could have electric fields having X and Y components too. And really the rule to get the electric field is to take partial derivatives. So what I mean by a partial derivative, if you haven't seen it before, is say I want to take the partial derivative of the potential with respect to X. Well, I hold every other thing constant except the variable X. I do that for the Y. This should be a Y here, and the Z variables, right? And those give me the components of the electric field. So for example, our expression for electric field there, derivative with respect to X and Y is 0. There is no X or Y variable here, but there is a Z. So if I take negative derivative with respect to Z of this potential, I will get only a K hat or Z component of the electric field. Taking the derivative, we won't go through the details, chain rule, all that stuff. You end up getting this expression for the electric field. K, capital Q, Z over square root of, or R squared plus Z squared to the 3/2. Now, you could have used the chapter 22 way and done a similar thing with electric field, and they actually do that in chapter 22, and they get this exact same expression. But one of the points I want to make is that if you can get the electric potential as a function of the coordinates, you can take derivatives, negative derivatives, to get the electric field. This is great because we like to talk in terms of scalars as much as possible. We don't have to talk about the direction. We just give that function or number instead of vectors, right? But it is true. If I know the scalar potential, electric potential, I can get the vector electric field by taking derivatives. Okay, last thing here, now that I know the electric potential, let's talk about energy, right? That's really physically what matters. So let's consider this problem. If a proton is shot directly at the center of the hoop, long z, now it's going to have a speed v. What is the distance of closest approach? How close does it get to the hoop? So again, we are assuming it's coming along the z and coming in toward, right? It's going to get somewhere close. It's going to be repelled because it's a positive charge being repelled by all of these positive charges. What is the closest z it gets to? I just use conservation of energy. Now, really, really far away, potential energy is 0, right? You're far enough away from the charges, you're not going to feel the force from that. So if you shoot the proton, it's going to have all kinetic energy, 1/2 mv squared to start with. Now, what I do then is that kinetic energy changes to potential, right? Kinetic energy goes away and potential energy increases. Now remember, the definition of potential energy as it relates to electric potential V is I just multiply by the test charge. So the Q here is the charge on the proton that's actually coming in. It's not the source charge, which is E, that 1.6 times 10 to the negative 19 coulombs. So all I have to do is multiply E by my previous expression for my electric potential. So here's my expression for electric potential. Actually, this should be 1/2. There's no z here, right? So it's actually KEQ over square root of R squared plus Z squared. But I just take the test charge times my expression for the potential. And then I could solve for Z. I won't go through the details of that algebra here. It's actually not that bad. But my point is that I can use conservation of energy once I know the electric potential. I just get potential energy by taking test charge times V. Okay, so hopefully that will help a little bit with the line charge problem, and there is a conservation of energy type problem in the homework. So we will go ahead and stop right there for now.